Hey, good morning. Today we are going to start the meat and potatoes of our class, which is circuit analysis. And so first up, we look at 4 techniques for the diode circuit analysis. Let's go here. All right. So we have a diode circuit here, one source, one resistor, one diode, 3 components in the circuit. And we're going to look at 4 different methods, 4 different analysis techniques to try and find the voltages and currents in the circuit. So the 4 techniques are load line analysis. First one, this is a graphical analysis. Mathematical model based on the equations. Ideal diode model is an assumption. It's by far the simplest of the 4. And the constant voltage drop model is an extension of the ideal diode model. Okay. Extension of the ideal diode model. So now let me ask you, what is circuit analysis, right? If somebody asks you to define circuit analysis is basically the process of determining the unknown quantities. In our case, we are analyzing electric circuits. So the unknown quantities are the voltages and the currents that are present in the circuit. So in the same manner, if you're approaching circuit analysis for a diode, what we are trying to do is find the values for the unknown quantities in the diode circuit, which for a diode circuit would be the diode voltage and the diode current. Okay, so circuit analysis of diodes is basically determining the diode voltage and diode current. So it's a VD and ID. All right. For this circuit, it's a series circuit. We apply KVL. And we can write an expression for the source voltage as the sum of the resistor voltage and the diode voltage, VR plus VD. Right. One single energy source transferring to the passive components. And so V is equal to VR plus VD. One single current flowing through the circuit, ID times RD, sorry, ID times R plus VD. That's our primary equation for the circuit. Okay. We will use this equation, we'll use this example for all 4, for all 4 methods. And it's the same equation again applied to all 4 methods. So let's take a look at load line first. What exactly is load line? Well, the load for the diode is the external circuit. In this example, if you're analyzing the diode, everything else is part of the load as seen by the diode. Okay, so load line is the graphical representation that you plot on the diode characteristics. Load line is the graphical representation of the external circuit. It basically illustrates or presents the external constraints placed on the diode by the external circuit. Okay, so this is the constraint placed on the diode by the external circuit. Okay, so it basically illustrates or presents the constraint placed on the diode. In general, load line analysis basically applies to diodes, transistors, FETs, doesn't matter what kind of electronic device is, we can have a load line analysis for any of those devices. So in general terms, we can say a load line defines the external constraints placed on the device. Okay, and we will see this again and again for the different devices. And the load line analysis, we are trying to find diode voltage VD and diode current ID. Okay, so we have two unknown quantities. How many equations would we need if you want to solve two unknown quantities? Two equations, right? So one equation is our standard diode equation, which is already plotted here. Okay, so one equation is our standard diode equation. The second one is the KVL equation that we obtained from our circuit. Okay, so it requires two equations. One is the diode equation, and the other one is the load line equation. And this load line equation can be obtained by using any of our analysis techniques, meaning apply KVL, apply KCL, Ohm's law. It doesn't really matter how you obtain it. Okay. In this case, KVL makes the most sense, so we wrote a KVL expression. The diode equation, as an engineer, you can obtain from the manufacturer, right? The diode characteristic, sorry, not the diode equation. The diode characteristic you can obtain from the manufacturer, or if it's not provided by the manufacturer, you can obtain it from at least the spec sheet and create your own. The manufacturer will provide you a spec sheet with all the relevant values, saturation current, transit time, junction capacitance, series resistance, all of those values will be provided. You enter it in the diode equation and you can create your own plot. Okay. As students, this will be provided to you. So as students, you don't have to worry about it, but as a working engineer, if it's not provided, you can create your own. And then for the load line equation, we have two unknowns, right? So this is already given. This is from the KVL expression for our example. And we can write V is IDR plus VD. The easiest way to find an answer if you have two unknown variables is to make an assumption for one of them and then calculate the other one. And the assumption, the easiest assumption to make is if the value is 0. So we would assume VD equal to 0 and find ID. And then we will assume ID is equal to 0 and find VD. Thus, we'd have 2 points, 2 values, one for VD, one for ID. You join those 2 points, you get what is known as the load line. The intersection point of the load line and the diode characteristic is basically known as the Q point. Q stands for, actually, let me get this out. The intersection point of these two is known as the Q point. The Q stands for quiescent. Let me see if I can spell this correctly. Quiescent. Yeah. Or more commonly known as the Q point. It is also known as the operating point for that circuit or for that diode. Quiescent means dormant. Okay, it is present but dormant. In the case of our electric circuit or electronic circuit, it basically refers to the bias point or the operating point of the device before the AC signal arrives. For our circuits, diodes, transistors, FETs, MOSFETs, we have both DC as well as AC. The DC is used to place a constraint on our device. Okay, this is the place where we want you to work, so you better be ready before the AC signal arrives. Hopefully that makes sense. And so it is known as the biasing. The biasing is always to do with the DC. Okay, so we apply a DC voltage and the circuit is in a dormant state before the AC signal arrives. So in this case, dormant does not mean it's not doing anything. It's basically applying the DC voltages to force our device or our circuit to work within a certain range of parameters. Okay, hence it is also known as the operating point. So again, depending on our application, that operating point could move anywhere on the device characteristic curves. The way we have a diode characteristic curve right here, for a transistor, for a FET, for a MOSFET, also we'll have a set of operating curves, characteristic curves. And the operating point for the device, for the circuit, can move up and down anywhere along that curve. Does that make sense? Right. So again, this is the diode characteristic without any constraints. And then we apply the DC voltage. We are telling our device to work only in a certain area of that curve. And the intersection point right there gives us the operating point or the Q point. So the values of the diode voltage at that point are labeled as IDQ and VDQ. So an additional subscript of Q is applied to the diode voltage and the diode current, hence IDQ and VDQ. And to analyze the circuit, we want to find the values of these two quantities. And that would give us the solution to the circuit. Okay. All right, let's take a 10-second pause. Let me know if you have any questions. Any questions from anyone? Okay. All right, let's solve this then. V, the source voltage is IDR plus VD. If ID is equal to 0, then VD is equal to V, which is equal to 10 volts. Right? ID is 0 and VD is 10 volts. If VD is 0, then ID is V over R. You get 10 divided by 10,000 or 1 milliamp. 1 milliamp. So far, so good. Right? We have our 2 points. We can now take those 2 points and plot it out on the chart. But the chart that is given to us only extends up to 6 volts. So this is, of course, a very simple circuit. If this was a much more complicated circuit and we're trying to plot it out, we just take the farthest extremes or take a point somewhere in the middle. So here the book takes 5. Let's take 6 and find the value for ID. So if VD is equal to 6, what is the value for ID? Well, ID would be V minus VD divided by R. So that would give me 10 minus 6 divided by 10,000. And it gives me a value of 0.4 milliamps. 0.4 milliamps. So now I have a point that is on the chart itself. Join the two and you obtain the Q point right there. Okay, and that gives us the value for IDQ and VDQ, diode voltage and diode current, when the source is 10 volts. Okay, if the source changes values, the operating point is going to move up or down depending on the value, but it'll always be on that curve. Okay, all right, let's take a 10-second pause. Think over it. Let me know if you have any questions. Yes. Oh, 5 volts. The 5 is basically the book exam. Yeah. So, and we did 6. Yeah. 5 would just be 0.5 milliamps. Yeah. 0.5 milliamps. So now, what are the actual values though? And here's the thing. As an engineer, we always start to find the exact value, right? But when you work with graphs and charts, we have to literally, we are eyeballing it. So you have to eyeball the values. So we look at it here. And if I wish to find the value of the current, what would you say the current is at this intersection point right there? You'd have to zoom in with eyes better than mine. But what do you think it is? Approximately. So this is 9 right here. And this is, you would say, what about halfway between 9 and 10, right? But it seems to me that if I just look at the point, it could be halfway between 9 and 10, but it seems to me it is probably slightly below the halfway mark. So when I said eyeball, the answer would be slightly different, depending on who's looking at it. IDQ could range from 0.94 milliamps to 0.95 milliamps. So 0.94 to 0.95. And again, the reason I state that is because it seems to me as if it's slightly less than 50% of that division. Does everyone see what I'm talking about? Right? As an engineer, you may be faced with this at your work. It's quite possible, right? If you're doing something on a graph or a chart and you need to get like a quick value out, this is something you need to do. So you probably have to develop your skill a little bit in eyeballing values, which is something I also do when I look at an oscilloscope. When we look at oscilloscopes, especially the newer models that have come out in the last few decades, we have an automated measurement system in there, but it's not always accurate because it adds up all the noise signals available. So I always want to look at it visually with my eyes and just manually calculate. That gives you a good and quick measurement. Obviously, you would back up that measurement. So something like this would be backed up with another analysis techniques. You would not be the only one working at it, right, as an engineer. As a student, if you're doing this kind of problem, I will ensure that the graph and the charts that you get, will not be too ambiguous. But if it is something like this, and one student answers as 0.94, another answers as 0.95, both values will get full credit. Okay, so as students, you don't have to worry about that. But if it goes above, if it goes like 0.96, then I can state that it's clearly not 0.96. It's either 50% or less than 50% of the way. So it's either 0.95 or 0.94. Does that make sense? So how about the voltage then? What do you think the voltage is? It is on the right side of the 0.5 line. So it is definitely not 0.5, right? So if we divide this up into 5 divisions, say 1, 2, 3, 4, that's like 5 parts. They're not quite equal. It's about 0.6 or maybe slightly less than 0.6 volts. What do y'all think? 0.55, yeah, I would give full credit to that. So I would say somewhere between 0.55 and 0.56. So VDQ would be 0.55 to 0.56 volts. Oh, not 0.56, sorry, 0.6 volts. And again, this is subjective. As an engineer, you would be faced with situations in your everyday, professional career where you have to make certain assumptions about certain values. So this is an example where you would do that. But as students, again, the goal is to train you. So as students, you need to learn how to do this, and you will still get full credit. All right, any questions? Load line analysis is not restricted just to diodes. We will see this technique again and again for the entire, the rest of this course. It's just one of the techniques that we use. Let's see, a couple of minutes left. I want to introduce the ideal diode model. So any questions before I move on? Okay, let's talk about this. Not the mathematical model, but the ideal diode model. In the ideal diode model, we make an assumption that the diode does not require any extra voltage to turn on. It's ideal. A real diode has a built-in potential, 0.6 to 0.7 volts, right, for silicon. In an ideal diode model, we say if the source voltage applied to the diode is slightly greater than 0, then the diode is on. And when the diode is on, in forward bias, it is replaced with a short circuit. In reverse bias, we say the diode is off. It is replaced with an open circuit. So this is the ideal diode model. And you would say diode is replaced with a short circuit. And in reverse bias, diode is replaced with an open circuit. And if it's a short circuit, then the diode voltage is equal to 0. And if it's an open circuit, diode current is equal to 0. Okay, that's the ideal diode model. We will look at these models later this week. For now, we will end class here today, and I will see you all on Wednesday. If you have any questions, I'm available. If you want to pack up, but there's a class after us, so let's clear out the room.
Thank you, Professor.